Finishing up Chapter 8, we have a named theorem here. DeMoive's theorem. And all this really does is it takes some complex number z to write it in its polar form, and we saw last time that if we multiplied these numbers together, if we had multiples of them, we would multiply the modula and add up the arguments. But if I do this to itself, I'm just going to be taking this and multiplying it by itself, and I'm going to be taking these numbers, whatever my thetas are, and adding them to themselves. So DeMoive's theorem tells me that z to the n is equal to the r to the n cosine of n theta plus I times sine of n theta. And that's where this polar form really gets exciting, just how powerful it is. Because if I wanted to take, let's say, let me find a good one here. One half plus 1/2 I to the 10th. Now you should know from a college algebra or a different pre-calc course how to multiply this out, but oh man, that's going to take forever. Raising it to the 10th power, that's going to take a long time. But if we write it in its polar form, we can get this done in a much shorter length of time. So if we want to start out by finding its modulus, 1/2 squared plus 1/2 squared, that works out to square root of 2 over 2. So we're good there. The other thing is that we're really looking, if we want to find its argument, we're looking for something where square root over 2 cosine theta equals 1/2. Square root over 2 sine theta equals 1/2. And we end up with cosine theta equals 1 over square root of 2, which is actually square root of 2 over 2. You get the same thing for the sine, and we see that the argument is pi over 4. So 1/2 plus 1/2 I is equal to root 2 over 2 cosine of pi over 4 plus I sine of pi over 4. And therefore 1/2 plus 1/2 I to the 10th power equals root 2 over 2 to the 10th power cosine 10 pi over 4 plus I sine of 10 pi over 4. And that can be computed pretty quickly. You get 2 to the 5th over 2 to the 10th cosine 5 pi over 2 plus I times the sine 5 pi over 2. Well, this is going to be 1 over 2 to the 5th. Now 5 pi over 2, that's going to be the same thing as pi over 2. So 0 plus I times 1, we get I over 32, and we're done. It may seem like a few steps to have to convert this complex number into its polar form, but I guarantee it's a whole lot shorter than trying to take this binomial and raise it up to the 10th power. Now, if we can take something and raise it to a power, we should also be able to get its roots. And this is the other part of DeMoive's theorem. If z equals, again, r cosine theta plus I sine theta, I'm going to let w sub k equal r to the 1 over n multiplied by the cosine theta plus 2k pi over n plus I times the sine theta plus 2k pi over n. And this is going to be called an nth root. And we're going to get one for each k in the list 0, 1, 2, out through n minus 1. So if n is 5, this list would be 0, 1, 2, 3, 4. If n is 10, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice there's n numbers here because we've included 0, which is where we get this nth root idea. But we're going to use the periodicity of the cosine and the sine function to help us compute these sorts of things. So what really it turns out to be, for these nth roots, the modulus is the nth root of r. Just using the standard nth root with real numbers that we can compute either by hand or in a calculator. But the argument starts at theta over n, which makes sense from DeMoive's theorem before. When we were taking something to a power, we multiplied it by n. Now we're going to divide it by n, but we're going to have to add 2k pi over n to each argument to get the next root. So let's do an example. Suppose I had z equals negative 64, and I wanted to find the sixth root of z. And there should be 6 roots. Now geometrically what's going to happen we're going to end up out here on a circle. And this is why we've got that 2 pi over n. We're going to end up finding all of these roots out on the circle. We're going to find them all evenly distributed around a circle. It'll be up to us to figure out what the radius of that circle is and what the angles are that are coming in between these two. So let's see if we can figure this out. If z equals negative 64, modulus of z is just 64. So we get z equals 64 cosine pi plus I sine of pi. And we look at these. Why did I choose these? Because sine of pi is equal to 0. So this will be I multiplied by 0. And there's no I up here. This positive 64 needs to get multiplied by negative 1. Cosine of pi is negative 1. So in the complex plane that we were drawing earlier, we've got the right argument, we've got the right modulus. And so now I need a couple of things. 64 to the 1/6 power, you can compute, is 2. So W0 is 2 times the cosine. Now what am I going to take the cosine of? I'm going to take this argument here, pi. Now I'm going to divide it by 6 because I'm taking the 6th root. Same thing over here. So I'm going to get cosine pi over 6 plus I times sine pi over 6 square root of 3 plus I. W1, 2. The argument comes, again, from this 6th root of 64. Multiplying it by a cosine again. Still going to take pi over 6 for starters, but I need to take that and add 2 pi over 6 plus I times sine pi over 6 plus 2 pi over 6. And I'll end up with 2 times the cosine, pi over 2 plus I times the sine, pi over 2. We just get 2I. And I can continue with these the rest of the way, and what I actually end up with, if we go back to our circle, root 3 plus I, there's 2I, negative root 3 plus I, negative root 3 minus I, negative 2I, and positive root 3 minus I. That nice symmetry distributed evenly all around the circle, and it turns out that we have a circle of radius 2. So that gave us this nth root, in this case the 6th root of z. The 6th root of the modulus, the fact that the modulus was 64 and the 6th root of that was 2, is why we ended up with a circle of radius 2. And then we just placed our roots all the way around, evenly split this up into 6 sections. I computed the first and the second one here. I can compute W2, W3, W4, W5, and they're all going to come from there. So with DeMoive, we can compute roots very quickly, and we can compute powers of complex numbers very quickly.